Hey guys, welcome back. I'm going to go over the solutions of the problems that are at the end of the gravity and orbits Phet. This one didn't load for some reason, so I had to write it out. But it says if you double the period of an orbit, how does the radius change? This could also be our semi-major axis, which would be A, the thing we substituted from an ellipse into a circle. So looking at our proportion, we know that T squared is proportional to R cubed, or the semi-major axis cubed. And so if I am doubling T, I have that 2 squared is proportional to R cubed, and so R would be proportional to the cube root of 4. I'm going to erase this and go to the next one. So I think on your guys' lab it was to the 1/3 power. If you double the radius of a semi-major axis, how does the period change? Again, same association. T squared is proportional to R cubed. So now I'm doubling this side. So T squared is proportional to 8. So T would change by a factor of the square root of 8, which is 2 radical 2. A planet has a mass double the Earth's and a radius 1/2 that of Earth. If a man weighs 600 newtons on Earth, on the new planet he weighs. So our formula is this GMM over R squared. We're saying that the new planet has a mass that's double and a radius that is 1/2. So this is squared, this is 1/4. 2 divided by 1/4 is 8. So 8 times 600 would be 4,800 newtons. A system has 3 parts located on the x-axis, 1 kilogram at 0 meters, 4 kilograms at 5 meters, and 6 kilograms at 7.5 meters. Where is the center of mass located for this system? So I'm going to do M1 X1 plus M2 X2 plus M3 X3 over M1 plus M2 plus M3. So this is going to be 1 times 0 plus 4 times 5 plus 6 times 7.5 divided by 1 plus 4 plus 6. So I got 5.9. So if this is 5, we could say that all of the mass is right about there. The acceleration due to gravity on a planet with a radius 1/6 that of Earth and the same mass would be, So this formula has to do with the gravitational constant, the mass of the body that is causing the gravitational field, and then the distance you are from the center of that body. So this isn't changing, this isn't changing. It's going to go up by 36 times. So on Earth, it's 10. So it's going to be about 360 meters per second per second. I don't know if we can see these arrows. I might have to draw them in. That's okay. I can do that. So I have a moon going around a planet. Draw in my velocities and my accelerations so we can see them. At this point, if it's going clockwise, so clockwise is this way, you would expect the velocity to be tangential. So the object is trying to go in a straight line. Its velocity is pointing in a straight line, so as it goes around, you would expect its velocity to be trying to go that way. As it orbits around, acceleration is centripetal. So that means that it is center seeking. And that gives us choice B as our best choice. A ball of mass M is attached to a vertical rod by two massless strings. The rod is rotated by its axis so that both strings are taut with tensions T1 and T2 respectively. The strings and rod form the right triangle shown in the figure above. The ball rotates in a horizontal circle of radius r with a speed v. What is the magnitude of the net force on the ball? So as this ball goes with this constant speed around in the y-axis, F net is 0. So part of T1 is going up and mg is going down. In the x-axis, it is F net equals mv squared over r. So we have 0 plus mv squared over r, which would just be mv squared over r. A 100-kilogram cart goes around the inside of a vertical loop of a roller coaster. The radius of the loop is 3 meters, and the cart moves at a speed of 6 meters per second. At the top, the force exerted by the track on the cart at the top of the loop, that shouldn't be circled. So my forces are mg and n, both going down. I'm going to do F net equals mv squared over r. I'm going to take forces towards the center, minus away. So this is going to be mg plus n is equal to mv squared over r. The force exerted by the track on the cart is n. So I'm going to have mv squared over r minus mg. So this is 100. This is 6 squared. This is 3. And then this is 1,000. Right? Because you have 100 times 10. So I have 36 times 100 would be 3,600. 3,600 divided by 3 would be 1,200. 1,200 divided by 1,000 would be 200. So the track has to provide 200 newtons of force down for this to be able to turn. A ball of mass M is attached to the end of a string of length L as shown above. The ball is released from rest at position P where the string is horizontal. It strings through position Q where the string is vertical, then position R where the string is horizontal again. What are the directions of the acceleration vectors of the ball at positions Q and R? All right, so something of note. At P, it stops, and at R, it stops. So it's starting here at rest, swinging, stopping again, going back, 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 back. I didn't mean to draw on that. When it's at position Q, you would have tension going up and weight going down. The tension would both have to accelerate it and balance out the weight. So you had to have a net force upward. So I can get rid of 3 choices. And then when I'm at R, when I briefly stop, I'm not in circular motion anymore. And so at that moment, if I did my free body diagram, I would have mg going down. They're trying to trick you into doing to the left, but there would be no force to the left until I started to go down. As soon as I leave that position R, there has to be a force that's starting to turn it. But at that point there, I'm not pulling on the string at all. There would be no tension at all. Two blocks are pushed along at a horizontal frictionless surface by a force of 20 newtons to the right, as shown above. The force the 2 kilogram block exerts on the 3 kilogram block is. We haven't covered that these internal forces, they're equal and opposite third law forces, but the amount that 2 kilograms pushes on 3 kilograms is going to be the same amount that 3 pushes on 2. So our question is, how much of the total force does 2 kilograms get? Well, it's going to get the amount of the total force that is related to its percentage of the total mass. And 2 kilograms is 2 kilograms of a total mass of 5 kilograms. So it's going to get 40% of the total force pushed on it from the 3 kilograms. So I have 20 times 2 fifths is 8 newtons. So that means 3 kilograms pushes with 8 newtons this way. That means that 2 kilograms pushes with 8 newtons that way. The same idea, if you push on a wall, it pushes back exactly as much as you do. You can also look at it as a 3 kilogram uses up a certain amount of mass, and it uses up 3 over 5, 3 fifths of the total mass, which would be 12. And then 20 minus 12 would give us 8. So we would have 8 newtons going to the left. If the magnitude F1 is the magnitude of force exerted by the Earth on a satellite in orbit around the Earth, and F2 is the magnitude of force exerted by the satellite on the Earth, then which of the following is true? These are equal. And we saw that in a number of places in the lab. They're equal and opposite forces. So why does the satellite go around the planet and the planet doesn't go around the satellite? Why does it behave different? It's because of the second law. So the second law tells us that F net is equal to ma. And this force, its effect is going to be determined about how big this mass is. And the mass of the satellite is so much smaller than the planet that that force has a big effect on it. Whereas the planet's mass is so big, that same force has almost no effect on it, or you could say no effect on it. And that's when we have circular orbits, if we have one mass that's much, much greater than the other. All right, that's to the end. That's the self-assessment.